Okay, class. Bismillahirrahmanirrahim. Assalamualaikum. So today we're going to have a guest lecturer from University Kebangsaan Malaysia to talk about Neyman Pearson Lemma, which is the last topic for our syllabus, right? So let me introduce Dr. Irfan, Dr. Muhammad Irfan Abdul Jalal. He is a medically qualified and highly dedicated medical statistician with 8 plus years of experience in applying various basic and advanced statistical methodology lah, including Bayesian statistic in clinical research, specifically in the field of oncology, therapeutic drug monitoring, right? He is highly proficient in complex data analysis and interpretation with expert knowledge in good clinical practice. And he also have extensive programming experience using R, SAS, and data analysis using commercial statistical platform such as SPSS, Stata, and Minitab. So he also has a significant publishing track, right? Track record and experience in postgraduate supervision and undergraduate teaching. Multitasker as evident from multiple role, assume and responsibility and trust during employment and study lah. So, Dr. Irfan, you can share your slide if you want, then and you can take over the class lah.
Okay, Dr. Nasir. Yep. Can you all see my slides?
Boleh.
Boleh ya? Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to all students. My name is Muhammad Irfan Abdul Jalal. I'm currently working at the Institute of UKM Medical Molecular Biology Institute, one of the research institutes in UKM, as one of the biostatisticians in charge of the Malaysian cohort project in here. My basic qualification, I'm a medical doctor with PhDs in mathematical statistics from Newcastle. I'm also a graduate statistician under the RISS and the American Statistical Association. So today we will be covering the Neyman Pearson Lemma, which is the final topic for your modules, I presume. And then we will kick off our lesson today with some introductions on Neyman Pearson Lemma, and then the lesson objectives. I mean, what we are expecting from the students to understand from today's lectures. Some recaps on the previous statistical theories that you learned, and then I will show some practical examples on several questions on Neyman Pearson Lemma. Okay. And then the methods of teaching of delivery. I mean, the method of delivery today. I mean, if you have any questions, you feel free to interrupt me, and then you can ask the questions at any time point during the lectures. And we will have like 5 minutes breaks after the lectures. After 1 hour lecture, and then if we haven't completed the whole teaching within that 1 hour, we will continue until the end of teaching at 12 noon today. Yeah. So let me start by explaining what is the Neyman Pearson Lemma all about. Because based on the classical or traditional frequentist theory of hypothesis testing, the things that we are learning at the moment, it is always is deeply rooted in Neyman Pearson Lemma, which means that the Neyman Pearson Lemma is the basic building blocks of the classical hypothesis testing paradigm that you are learning at the moment. So without this Neyman Pearson Lemma, there will be no like all these classical hypothesis testings and all these p-values and all this kind of things that we learn since the past few weeks. I mean, it will not exist. So this Neyman Pearson Lemma can be considered as the building blocks, as the most important building blocks for the traditional statistical theory. So under this paradigm, we try to limit ourselves or try to restrict ourselves to test statistics. I mean, I'm sure that you understand what is test statistic all about, for which the probability of type 1 error is less than or equal to a specific constant alpha. So we try to restrict the test statistics where the probability of committing the type 1 error will be equivalent or will be at least equivalent to a specific constant that we fix at alpha level. And then the critical region, or in other words, we can also call the critical region as the rejection region for testing a simple null hypothesis. Theta equals to theta naught, not theta a, is said to be the best. It's said to be the best or the most powerful if the the simple alternative hypothesis is said to be the best for the most powerful or the most powerful if the power of the test at theta equals to theta a is at the max maximum. Means
Dr.
that the
Irfan,
yes.
slide ada bertukar ke?
Huh?
Slide macam tak berjalan.
Oh, tak berjalan eh? Okay. Nampak berjalan tak?
Tak berjalan. Dia just
tak nampak.
Okay, sekejap. Okay, boleh nampak slide ke? Hello?
Boleh nampak slide. Tapi try ni slide show. Dah slide show ke?
Kat sini ya, slide show kat sini.
Okay.
Nampak ke?
Tak.
Nampak
Maybe Dr. Irfan boleh share the whole screen kot. Instead of sharing the PowerPoint instead kan?
Kalau buat macam ni tak nampak Ini macam ni nampak ke?
Macam ni okey lah. Jalan.
Okey. Ni nampak kan?
Nampak.
Ni nampak? Tak nampak?
Ada move to slide number 2 sekarang kan?
Yang type 1 tu error tu nampak? Tak nampak?
Tak.
Tak nampak. Sharing sekejap. Saya stop sharing sekejap. Okay, ni boleh nampak?
Cuba jalan.
Saya besarkan sikit. Okay.
Besar sangat. Boleh.
Besar sangat.
Okay.
Okay. Alright. So saya repeat balik lah. And tadi, so because as a recap, our current classical traditional frequentist theory is based on Neyman Pearson Lemma. So because of this, it's crucial that the practitioners of statistics or the students or statistics students to understand what this Neyman Pearson Lemma is all about. Under this Neyman Pearson Lemma, we try to limit or restrict ourselves to a statistic where the probability of type 1 error is less than or equivalent to a specific constant alpha. Because in this case, we fix the alpha and then we try to limit the statistics to values to an alpha values to a fixed alpha values. So in this case, we can define the critical region or the rejection region for testing a simple null hypothesis against an alternative hypothesis of theta equals to theta a, and which is can be said to be the best or the most powerful if the power of the test at the theta a or the values of theta under the null hypothesis is at the maximum, which means that the power is the best or the maximums at theta a. This is for a simple null hypothesis. So as a quick recap of the things that you have learned before, let's look at this table. For example, we have a result of the hypothesis test. And then these results can be classified or categorized into two. Whether when we perform the hypothesis test, we might either manage to reject the null hypothesis or fail to reject the null hypothesis. But the truth, I mean, the actual truth about the experiments or about the test is either the HO is actually true or H naught is actually false. So, if the result of the hypothesis we fail to reject the null hypothesis is actually then H naught is true, then we can say that we make a correct decision because we don't reject the H naught and the H naught is true, so it's a correct decision. And this 1 minus alpha can be considered as our confidence about the process. And then there's another scenario is we fail to reject but in truth, not is false. It's actually, H naught is a mistaken belief. We can call that. In this case, we commit a type 2 error, or in medical term, we can call it as we commit a false negative, and this is signified by this symbol beta, and which usually used in this notation beta as a type 2 error. So in the other scenario, when we conduct the hypothesis test, we manage to reject the null hypothesis. But actually, in truth, in the state of nature, actually, the H naught is true. And in this case, we commit a type 1 error, which means that we commit a false positive results. Actually, we got a positive result in here, but actually the real truth is actually there is an actual negative result here. So it's positive and it's negative, so actually we commit a false positive result. So the last scenario is if you manage to reject the null hypothesis based on the hypothesis testing, based on the hypothesis test that we carried out, and then the actual H naught is false, and in this case we can accept the HA or the alternative hypothesis. In this case, we make a correct decisions, and this can be considered as the power of the test, which means that we managed to detect real statistical difference, a significant difference, where the difference is actually exists in the state of nature or in truth. Okay. So after this, we want to see what the relationship between the alpha and beta and the different null and alternative distributions, hypothesis distributions. So we can say that under the null hypothesis distributions, this is our 1 minus alpha, and then under the alternative hypothesis distribution, or H1, in using this notation, this region can be considered as our power. It's a 1 minus beta, and then the type 2 error rate is given by beta here, the shaded region here, the green shaded region here, and then the type 1 error is given by the blue shaded region in here. As you can see, if we move the line here to the right or to the left, we can either if we move the line to the right, so we will reduce the type 1 error alpha, but at the same time we increase the type 2 error. But if we move this line to the left, then we will increase the type 1 error, but we can reduce the type 2 error. So in this case, there's a slight inverse relationship between alpha and beta. You cannot really reduce both. So if you increase one of the errors, so it will reduce the other one of the errors. Okay, so there should be a trade-off. We call that a trade-off, where we fix alpha at certain point, but at the same time we try to maximize the power. That is the basic theory of a Neyman Pearson lemma. Try to find this kind of region that can maximize the power while maintaining the alpha level at a pre-specified size, at a fixed size, usually at around like 0.05. So the objective of this lesson today is to find the most powerful region of size alpha, which is H naught. For example, H naught equals to theta equals to theta naught, and HA, the alternative hypothesis where theta equals to alternative theta A. But before we proceed with our lesson, we need to set some rules for our lesson today. So I will introduce some notations, and the differences between a simple and composite hypothesis, and defines what it means to have a best critical region of size alpha. Size alpha can be considered as your type 1 error. When we say size, it means that you're some sort of like your type 1 error. So these are the notations that I will introduce today. For example, let us consider we have a sample, the sample from a distributions like x1, x2 until x3 until xn and so on and so forth. From a distribution, either continuous distribution like which is based on the probability density functions, or like a discrete distribution which is based on the probability mass functions, given by this function, by this mathematical function fx given theta. Then the joint probability or probability or mass functions of x1, x2, and xn, which are the random samples of size n that you obtain from the population, it can be denoted by the likelihood function. Likelihood here. So L theta is like it can be considered as a composition of likelihood of the parameter theta given your sample, the information that you have in your sample, the x1, x2, x3 until xn, and then this is given by these equations, where here means that the products of the distribution for each of the sample here, x1, x2, and x3. So this is this product. The term is called as product. So which is equivalent to f x1 given theta times f x2 given theta until f xn given theta. So this is considered as your likelihood functions. It is crucial for us to remember that the likelihood is still dependent upon on the observation or data in the sample. It means that the likelihood here, the likelihood of your parameter here, like your mean, your standard deviation, your variance and other parameters like your scale or rate parameters for exponential distributions, all this kind of things, is the values here is dependent on the informations given by the sample in your data. By the sample here, in your data, the information in here. That's the meaning why we need to always remember, or we need to believe that the likelihood is dependent on the information contained in the observations or the data in your sample. So now we'll introduce the definitions for simple and composite hypotheses. So for example, we have a random sample taken from a distributions, from a PDF, from a continuous distribution with a PDF, blah, 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 with parameter theta. We can say that hypothesis, we can say that hypothesis can be classified into two. The first one is simple hypothesis, which means that the hypothesis uniquely specifies the distributions of the population from which the sample is taken from. Which means, meaning that if we really, meaning that, I should give you an example. If we have a normal distribution or a Gaussian distributions, which the same thing, normal and Gaussian distributions, where we specify the mean and then the variance equals to certain value. For example, mean equals to 3 and then the variance equals to 16, for example, then the hypothesis, then these kinds, the simple hypothesis that actually specify what are the values of the parameters. In this case, mean equals to 3 and then variance equals to 16. Is considered as a simple hypothesis, because when we plug in all this value, the mean and the mean equals to 3 and the variance equals to 16 into the PDF of normal of our normal distribution, then we can get an exact distribution of normal we can get an exact PDF for a normal distributions with mean 3 and variance 16. But there's another type of hypothesis, which is a composite hypothesis. This is a hypothesis that is not a simple hypothesis. For example, using the normal distribution analogy example, if for example we just specify the mu, the mean parameter as equals to 3, but we don't specify sigma squared or your variance parameter to any values, then the distribution is not exact anymore. The PDF is not exact because the variance can take any values from, from zeros until positive infinities. In this case, the PDF is not exact, and then the PDF can take any, can take different forms depending on the values of the variance. So in this case, the hypothesis is no longer simple, because it doesn't conform to any actual PDF. In this case, we consider this one as a composite hypothesis. So illustrate this further, let's do some example to highlight or to illustrate the differences between the simple hypothesis and the composite hypothesis. In this example one, suppose that we have a random sample here, x1, x2, and until xn, from an exponential distribution with a parameter theta. So in this case, we specify the alternative hypothesis as theta equals to 3. So the question is this a simple or composite hypothesis? So we need to answer these questions. Whether HA theta equals to 3, a simple or composite hypothesis. Okay. Can I make the screen larger a bit? Can you see this slide?
Boleh.
Boleh ya? Okay. Okay, so I have to magnify the slides a bit. So in this, the solutions for this example, we have to obtain the key information first. Just say that we have a random sample from an exponential distribution, the x1, x2, x3.
Dr. Irfan, boleh besarkan sikit? Tak nampak sangat.
Besarkan sikit
besarkan sikit.
Right. Sekejap. Still kecil ke?
Okay, boleh.
Boleh. Saya nak besarkan lagi sekejap.
Okay. Okay, nice.
Okay.
Nice.
Okay. Alright. Okay. So we need to obtain the key informations from the question first. So we can say that we have a random sample x1, x2, x3 until xn. So this random sample can be considered obtained from an exponential distributions, as you have already learned from your probability theories before, from your distribution theory before. The PDF, or the probability density function for an exponential distribution with parameter theta, is given by these functions. Fx equals to 1 over theta, exponential of minus x over theta. And then the x, the support for x is more the zeros and zeros until some values, until infinities. And then the parameter itself, the theta here is more than zeros. So we need to specify both the support x and then the theta, so that we know the ratio of the values that can be taken by x, by your observations, by your data, and then the parameter. So under HA, under the alternative hypothesis, which is theta equals to 3, so we plug in this theta equals to 3 into your PDF here, so we will get these equations. We put the 3 here and then 3 here, and then we get the PDF here. So for x equals to or more than zeros. In this case, we already nicely specify an exact distribution, an exact PDF for these exponential distributions with a rate of 3. With a rate of 3 with a parameter of 3. So the PDF gives a specific distribution of the population from which the sample is taken. Because this PDF is exact, it's very nice and exact, so it can be considered, this HA can be considered a simple alternative hypothesis. Because if we use this PDF, we can easily make an inference about the HAs and all those things. Because all the parameters values are specified. So it can be considered as a simple hypothesis. This is some additional infos for those who are interested. This parameterization of exponential distributions is based on a scale parameter. But the exponential distribution can also be parameterized using a rate parameter, and using this based on this PDF here. But this will not be examined, but I think it's just a nice information to be shared with the students. And then it has a memorialist property. So in case that maybe later on, after you finish your diploma and then you will go into degrees, into your degree, maybe doing your degrees later in statistics, this property is very important, the memorialist property, especially when you are learning the stochastic process, the queuing time, all those things, the queuing time, all those kind of things. And then if you learn survival analysis, because these memorialist properties, will be used many times in survival analysis to prove certain properties of survival models, especially the parametric survival models. So we go to example 2 now. Suppose that we have a random sample from an exponential distribution with parameter theta. So now we have HA that we define as a theta more than 2. So we want to know whether HA, the alternative hypothesis, now is a simple or a composite hypothesis. Okay. Oops. Maybe it doesn't. Tadi masa saya gerakkan slide tu, ada slide tu gerak ke tak? Tak gerak eh?
Yang tadi, ni bergerak lah.
No?
Yang ni bergerak.
Okay, saya bagi kat sini dulu. Suppose we have a random sample from exponential distribution with parameter theta. So in this case, we want to know whether this HA or the alternative hypothesis theta more than 2 is a simple or composite hypothesis. So the solution for this example is given here. Okay, so in this example 2, so we recall that the exponential probability density function is given by this function. Have been shown before in the previous previous solutions. So we put the we put the support of x as equals to 0 or more than 0, and then theta more than 0. So h naught can be any values more than 2. So theta can take a value of 3, 4, 5, so on and so forth until values of n. So if we use different values of theta here, 3, 4, 5, or n, so we will obtain different PDF. Here we have the PDF of these 1/3 exponential of minus x over 3. And PDF fx 1/4 of this, and then 1/5 exponential of times exponential of minus x over 5, so on and so forth until if we specify the theta n as theta equals to n, then we get this kind of PDF where it is 1/n exponential of minus x over n. In this case, we don't really have a one nice PDF just to represent our alternative hypothesis. It can be any of these PDF because the theta value is no longer exact. It's no longer fixed to an exact value. In this case, we can say that the HA or the alternative hypothesis is a composite hypothesis because it doesn't conform to, or it doesn't belongs to any to an exact distributions. It can belong to any types of any kind of exponential distribution. Depending on the values, the actual values of theta that the parameter will take. Okay. So this is okay. Let me show you the example 3. So this is quite a trick question. Suppose that we have a sample x1, x2, and txn, a random sample from a normal or Gaussian distributions with mean mu and unknown variance sigma squared. In this case, we don't know the variance, but we have a hypothetical value for mean mu. So if we say that if we fix the HA mu equals to 12, is this a simple or composite hypothesis? Okay. So based on the solutions in here, we need to extract certain key information from the questions. The first thing is we know that the samples come from Gaussian or normal distributions with mean mu and variance that are unknown. That the variance and then a variance which is unknown, and that I fixed to some value of sigma squared here. And then we say that the alternative hypothesis mu equals to 12. So recall that the PDF for a Gaussian distribution or normal distribution is given by this function fx, and then this is semicolon here is means that given your parameter here, which is your mu and sigma squared, equals to this kind of function here, where the support of the x can be from the minus infinity until positive infinity, and the variance should be should be positive. I mean the variance cannot take a negative value. I mean, it doesn't make sense. So when we specify our alternative hypothesis mu equals to 12, then the distributions under the alternative hypothesis is now given by this function, where the xi here equals to mu equals fx given by mu equals to 12, and then some unknown values for sigma squared. So we get these kinds of we get this kind of PDF for HA mu equals to 12. So as you can see here from the PDF here, you see that everything in mu has been specified nicely here, but as you can see here, sigma squared we haven't specified anything, any values. We haven't fixed any values for sigma here, the variance here and the standard deviation here. We haven't fixed anything, any values here. So we can say that this normal distributions PDF doesn't conform to any specific normal distributions. So because the sigma squared here, the variance here, can take any values. So in this case, the distribution is not fully specified since sigma squared is unknown. Hence, the alternative hypothesis of mu equals to 12 can be considered a composite hypothesis. Okay. So we have covered the first bits of our lecture today. The first part of our lecture today was about the differentiating between a null and a composite hypothesis. Before I proceed further, do you have any questions, or do you have any queries on this, or should I just proceed to the next part of this lecture?
Student, do you have any question? Please respond.
Please respond.
No, doctor.
No, doctor.
All right.
Okay. So I just carry on with the next part of the lecture. Okay. So now the second part of this lecture, we want to define what is the best critical region of size alpha. Okay, the critical region means that the rejection region where our values of our test statistic, if it falls in that region, then we can reject the null hypothesis. So, I mean, that's how I can simply explain what does it mean. But let's look at the definition first. So definition of this thing, of this best critical region of size alpha is, we suppose that we consider a null hypothesis, H0, where the theta equals to T0 here. And then we want to test your H0 against your alternative, against another alternative hypothesis where we fix HA theta to another values of theta A. So let's say that we have two critical regions, two competing critical regions of size alpha, which means that we have we fix the alpha to some values, maybe around 0.05, and then alpha is given by C given theta 0, theta naught, and then the type 1, and then the alpha equals to P probability D given by theta naught as well. So we have two competing regions here. One region is called C, and then the other region is called D. So we're testing against this theta naught, right? So which regions that we can select so that we can fix the size of alpha, but at the same time we can maximize the power, or in other words, we can minimize the beta or the type 2 errors. So based on these definitions, C is the best critical region of size alpha if the power of the test at theta equals to some values under the alternative hypothesis is the largest among all hypothesis tests, which means that if we have like 2 or 3 or 4 and so on and so for critical regions, we have to select the critical region where the alpha, the type 1 error or your type 1 error is fixed to that value. It doesn't like further reduce or something like that. It's always fixed at a certain value, but at the same time, we maximize the power of the test. Or in other words, we fix the type 1 error at certain value, but at the same time, we minimize the type 2 error. Because power is equivalent to 1 minus type 2 error. Based on the recap that I showed in the previous slide. So more formally, we can say that the best critical region of size alpha as if for every other critical region D of size alpha, P or PC, the probability of C given theta is bigger or size higher than P probability of D given theta naught. That is, C is the best critical region of size alpha if the power of C is at least, and this is the key words here, is at least as great as the power of every other critical region D of size alpha, which means that the power of C for this critical region is at least equivalent to the power of every other critical region D of size alpha, or it can be bigger than the power of every other critical region D of size alpha. So that's what I mean, that the best critical region is where we maximize the power. We maximize 1 minus beta, or we minimize the type 2 error, or beta. We may say that C is the most powerful test of alpha size because we fix alpha to certain values, the type 1 error to certain values. So we will move to the most important bits of this lecture. It's about the Neyman Pearson Lemma. Neyman Pearson Lemma, is based on works of two very famous statisticians, Jerzy Neyman and then Egon S. Pearson. Jerzy Neyman is a Polish statistician, a very eminent statistician. He's a recipient of the gold medal from the Royal Statistical Society UK. He's a probabilist, very good in probabilities, but at the same time he's one of the, can be considered as the founder of the classical statistical theories. And then this person here is Egon S. Pearson, who is the son of Carl Pearson, the famous Carl Pearson, who invented the chi-square test and other things. And then these two, and he's a British statistician. These two persons, they collaborated together, and then they came out with the Neyman Pearson Lemma, which was published in 1933, long time ago. It's nearly like 100 years ago. So these two persons can be considered as the founders of the current classical, classical or traditional hypothesis testing, right? So what is the Neyman Pearson Lemma all about? Okay, this is very important for you to understand. Suppose that we have a random sample of x1, x2, x3, and xn from a probability distribution with parameter. Sorry. Okay, right. Okay. All right. Suppose we have a random sample x1, x2, x3, and xn from a probability distribution with parameter theta. So then if C is your critical region or your rejection region of size alpha, you fix your type 1 error to certain values here, and K is a constant such that the likelihood of theta under the L naught, under the likelihood of theta under the null hypothesis divided by the likelihood of the parameter or your theta under the alternative hypothesis is equals to or less than K. If you get the values of this quantity here less than K, so we can say that it is inside a critical region or inside a rejection region. So in this case, if this occurs, then we can reject the null hypothesis and somehow we accept the alternative hypothesis. If it's less than K means the certain constant here. But if the ratio between the likelihood of the parameters given your data under the null hypothesis against the likelihood of your parameter theta under the alternative hypothesis is more than k, then it's outside then the values, the quantity here is outside your critical region. So when it's outside the critical region, it means that it's in the acceptance region. So when it's in the acceptance regions, then you have to accept the H naught. Or in other words, in better words, we can say that we failed to reject the H naught. Okay. So then C can be considered is the best, that is the most powerful critical region for testing the simple null hypothesis, H naught theta equals to T naught against the simple alternative hypothesis HA, or theta equals to some values under the alternative hypothesis for theta. In plain English, we can say that Neyman Pearson Lemma considers an optimum test is a uniformly most powerful or UMP test of a given significance level or size alpha. Okay, so the most important bit is to understand these two, we call that these two inequalities, and then know how to apply these two inequalities, using the examples that I will show you after this. Okay, so as a recap, let me repeat it again, that if this quantity here, the ratio of the likelihood under the some values under the null hypothesis for your parameter against the likelihood of your parameter under the alternative hypothesis is equivalent to or less than k, some constants, then it's inside your critical region, inside your rejection region. And because of this, we can safely reject H naught at certain, a certain significant level of size alpha. But otherwise, if this quantity here, the ratio here of this likelihood against this likelihood is more equivalent to or more than k, which means that it's outside the critical region, so it is within the acceptance region, so we accept H naught, or in other words, we can say that we failed to reject H naught. All right. So these are the most important bits that you have to understand for Neyman Pearson Lemma. So if you want, we can proceed to example 4, or you need like a 5 minutes break first before we proceed with the example. Should we proceed, or you need like 5 minutes break, or you need you
Student,
want to
respond,
ask me any
please.
question? Please respond.
You have any questions so far? Or you want 5-minute breaks?
Or you want 5 minutes break?
I guess that 5 minutes break should be okay.
All right. Okay, then we will continue at 10:50. Is it okay then? Okay. Please have your 5 minutes break. Yeah. Assalamualaikum and very good morning. Can we start now? Is it okay?
Okay.
Okay. All right. So in this so we carry on with our lectures today. So this part we will continue with I will continue by showing you the examples how we can solve certain problems in hypothesis testing using Neyman Pearson Lemma. So in this example 4, suppose we have a single observations from a population with probability density functions of fx equals to theta theta x theta minus 1, where the support for x, the values of x can take from 0 until 1, and then the theta it's between the theta is between like 0 to infinity, positive infinity, for example. So find the test with the best critical region, or find the most powerful test with alpha or your type 1 error fixed at 0.05 for testing the null hypothesis, where we fix the theta naught here. Yes, I forgot the knots here. The theta knots here equals to 3 against the alternative hypothesis, where theta A equals to 2. Yep. Okay. So how can we solve this problem? Okay, I will show you the solutions. Okay. Let me increase the size a bit further. Yeah. Okay, so the solutions for this example, again, we have to follow these steps. For example, we have to check, the first thing is we have to check the hypothesis, where we get the informations from the question where the H naught is is specified as theta naught equals to 3, and then HA specified as theta A equals to 2, and then because the theta 0 and theta A, they assume certain values which are 3 and 2, so this can be considered as a simple hypothesis. So we can apply the Neyman Pearson lemma, which is this one. Then we can apply these relations here. By using these quantities, where likelihood of theta naught divided by likelihood of theta A, the theta values under the alternative hypothesis, which is equivalent to 3x squared divided values into the PDF of this of this function here, of this distribution here. So because of that, then we get this quantity 3x squared divided by 2x, and then by simple algebraic simplification, we get like 3 over 2x, and then this is equivalent or less than k. This is the crucial equality.
Dr. Irfan, tak nampak dia punya solution.
Ini tak nampak ke? Nampak?
Boleh turun bawah sikit. Dia nampak sampai L theta naught bahagi dengan L theta A.
Sampai situ je nampak. Okay. Right. Kalau saya tunjuk macam ni boleh tak? Okay. Macam ni Okay. Other than slideshow lah, saya tunjuk macam ni. Okay. Okay. So we got till here. We got the answer as 3 over 2x. Less than or equals to k, which is this is the inequality. So since like k is a constant, So we can consider the right-hand side as a, as a constant. So we can say we can replace this value with C. Representing the constants. So we can say now the rejection region is X equivalent to and then X is less than or equals to C. So the step 4, we need to find C now. So how we can find the C? So from the question, we know that alpha is equivalent to the probability of committing type 1 error, and then alpha we fix at the value of 0.05. So probability of type 1 error is equivalent to probability of rejecting your null hypothesis given the null hypothesis is actually true. Mean that they commit some sort of like you commit a false positive error in here. So how we can convert this into a mathematical relationship, into a mathematical relations. So it's equivalent to a probability of X less than C, your rejection region here, from here, probability of rejecting the null hypothesis, which is in here is your critical region. Reject the H naught, given the H naught is actually equals to 3, which is under your alternative, under your H naught here. Okay. Which is H naught is considered true in this case. So based on this, because to obtain this this quantity, we need to we need to integrate it to get the to get the distributions functions or the commutative distribution functions of this from C until 0, because the support for the support of this, the distribution function for this, the support is between C to 0. So we can fix that the alpha to 0.05, and then we integrate the 3x squared here, the density functions under the null hypothesis here with respect to x, dx. So based on a very simple integration, we can get x to the power of 3 with limits at C and zeros. So we plug in the limits C into x, so we get C to the power of 3, and then we put 0 is still 0, so C to the power of 3 minus 0 is still C to the power of 3. So this one is equivalent to 0.05. So to obtain what is C, so you need to take a cubic root in here, and then you will get a C equivalence to 0.368. Okay. So we, as a conclusion, in this case, we can say that the Neyman Pearson Lemma tells us that the rejection region, or the most powerful test of hypothesis H naught, where theta naught equals to 3, and then the alternative hypothesis where the alternative, the values for this theta under the alternative hypothesis is 2, is equals to x less than or equals to 0.368. So if the values of your x falls below 0.368, so it can be, the null hypothesis can be rejected. But if it's more than 0.368, so it falls within the acceptance region, so the null hypothesis cannot be rejected. Or we can say that it failed to reject the null hypothesis if your x, or chemical statistics, is more than 0.368. Okay, so there's the take-home message, the most important bits. So if it's less than or equals to 0.368, then reject it, reject the null hypothesis. If the other way around, otherwise, then you fail to reject the null hypothesis, or you accept the null hypothesis, because the values of x falls within the acceptance region. So this is another example here, example 5. In this scenario, in this case, we have again a random sample from a normally distributed quantity of interest. This is the clue. It comes, this samples comes from the normal distributions, and then it represents some quantity of interest, which can be anything, maybe your blood pressures, maybe your cholesterol level, all these kind of things, any continuous quantities from a population of people with mean, mu, and variance 16. So we specify the variance here. So you have to know, the clue is we specify the variance, but we want to test the mu. So find the test with the best critical region, i.e., or in other words, find the most powerful test with a sample size of 16, n equals to 16, and a significance level or set or fixed at 0.05. I mean, the significance level, I mean, can be considered your type 1 error rate fixed at 0.05. To tell you a simple hypothesis of H0 mu equals to 10 against H0 mu equals to 15. Okay, so how do we solve this kind of of problems? So let me show you the solutions. Remember that the PDF of a normal distributions is equivalent to these equations, to these functions. Okay, all these things. So the first informations that we need to hello. So the first informations that we obtain from the question is we need to specify what are the null and the alternative hypotheses. So mu equals to 10 under the null hypothesis and mu equals to 15. And then in this case, we specify the sigma squared as 16, the variance as 16. So again, we apply the Neyman Pearson Lemma, where we want to look at the ratios between the likelihood of the parameter under the null hypothesis against the likelihood of the parameters under the alternative hypothesis. And the parameters here is your mu. So in this case, the mu equals to 10 for under the null hypothesis, and the mu equals to 15 under the alternative hypothesis, whether it's less than or equals to some constant in here. Recall how we can obtain the likelihood for the parameters theta under the null hypothesis. So again, remember that the n equals to 16. So to obtain this one, we need to consider the joint distributions of all these 16 observations under the null hypothesis. In this case, mu equals to 10, and then the sigma squared equals to 16. So we can write it like this. This is the product. It's the product symbol for I from I equals to 1 until 16. So we have like 16 observations. So we have to multiply the density functions x1 given by given 10 for mu and then 16 for variance, and then multiply by the PDF of x2 given by given 10 for mu and 16 for variance until the PDF of x16. Your observation number 16 for a given mu 10 and variance of 16. So after some algebraic manipulation, you will get this quantity. So this one is 4, which is equivalent to the variance of 16 here. Because we plug in the 16 into the sigma squared here, and then 4 for sigma here. So we got this kind of quantity. Okay. So how about the likelihood of the parameters under the alternative hypothesis? Again, you do the same thing, but in this case, we fix the mu to 15, because under the alternative hypothesis, mu is now 15, and the sigma squared or your variance is still the same. It's still the same, which is 16. So the likelihood under the alternative hypothesis it takes the following form here. Okay, this is to the power of 16, because we just multiply everything, all the density function based on the joint probability, joint density functions of all these quantities for the 16 observations. Okay. So to get the likelihood ratio in here, this is called a likelihood ratio. The ratio of likelihood of your theta under the null hypothesis against the likelihood of the theta or mu under the alternative hypothesis is given by these quantities here divided by this quantity here, which is equals to or less than k here. So we get this kind of things based on the Neyman Pearson Lemma. Oops. So because this quantity are pretty the same, so we can cancel out this term. So only these two terms remain, and then it's still like 16 here. Again, and then when we cancel out those constants, this constants here, we cancel out the constants, so only this quantity remains, and then we means less than or equals to k. And these are the clue for the next step, where we have xn, when xn times xm, so it is equivalent to x n plus m. Okay. For this one, for this one, because we need to divide this quantity, the numerator with the denominator, we have like x n minus m. So we have to use this following algebraic rules. So the power here, we minus with the power here for this exponential term, based on this algebraic rule, where xn divided by xm to the power of m equals to xn minus m. So where we have this quantity here, the same quantity here, so we minus the quantity here, yep, the underneath it, yep. Right. So after that, we we expand the term inside the bracket here using like quadratic expansion. So we will get xi squared, I mean, with sum between observation 1 until 16 as I squared minus 20 with times to the sum of observation 1 until 16 for xi, and then for this constant here minus this following term, because we also expand the quadratic quantities here using quadratic expansions, and then we get the results here. Because this one is constant, and then this is summations between 1 to 16. So if we like sum hundreds up to 16 times, so we get 1,600 here. So if we sum 225 up to 16 times, so we get 3,600 here, because these are the constants. So after simplification, algebraic simplifications, we will get these following quantities, right? So how we can solve this quantity here? So we need to take logs, the natural logs on both sides, on both the left hand side and the right hand side. So this one becomes a ln k, and this one becomes a log of this quantities here. So log of e equals to the power itself. So we can remove the e here. So we get this following quantities remaining with which is less than or equals to ln k. So after some manipulations, we can bring this quantity to this side by multiplying both sides with minus 32. So this one becomes a minus 32 ln k, and then only the terms inside the bracket here remaining on the left hand side. Because we minus both sides with negatives, so the sign changed now from less than or equals to greater or equals to sign, because we multiply both sides with negatives. Okay, and then we bring minus 2,000 here to this side. So so the final form, we have this, we have this following quantities here. All right. Because we bring this one to this side, so it becomes a positive. So how we can solve this part? Again, there's a clever algebra. We can use some clever relationship between means and all those kind of things to solve these equations. As you know that the formula for mean is sum of xi sum of I equals to 1 to n for a random variable xi divided by its number, the number of the random variables, and we can get the mean here. So we know that our n is 16. So just imagine that if we just divide both sides with 160. So in this case, if we divide on the left hand side with 160, so it will be cancelled here. So we have like xi divided by 16. Okay. So when it becomes like this, so it's equivalent to the mean formula here, the blue one. So this one becomes the becomes the mean, or we can say that is your X bar here. And then we also divide your right hand side with 160. These are some clever manipulations of the inequality. So in this case, we will now get the left hand side becomes the mean, and this side becomes this quantity minus 22 times ln k plus 2000 divided by 160. But because we have a constant in here, so this can be considered as a fixed quantity because we don't have any random variables in here. So we can represent the quantity on the right hand side as C. So we can say that the critical region is your X bar. I mean, I forgot the bar here. X bar, your critical region is given by your X bar here, greater than or equals to or greater than C. Okay. This is the first part of the solutions for this problem number 5. Okay. Now we want to find the quantity for C. What is the actual value for C? All right. Just imagine, recall that your probability density function for normal distribution has the following shape, and then we have a support for x between your minus theta until your positive theta in here. So this region represent the alpha, your type 1 error as 0.05. This is your standard normal distributions with mean zeros and a variance of 1. Okay. So just imagine that alpha is equivalent to the probability of committing type 1 error. In this case, we can formulate this probability into a probability of rejecting the null hypothesis given the null hypothesis is true. So the probability or the rejection region or the critical region for H0 for this case is X bar equals to or greater than C based on the solution that I showed you just now, given mu equals to 10. Okay. So this quantity, this quantity can be considered as a variable, as a random variable from a standard normal distribution. So using Z, so this one is equivalent to Z values of these transformations of the into a standard normal variates or standard normal variables, which is C, the random variable C minus the mu, and then divided by its standard error, which is the sigma squared divided by n squared, or the sigma divided by square root of n. Okay, which is equivalent to 0.05. Okay. So if you look at from your Z table, from your standard normal table, then you will know that this quantity is equivalent. The Z value here is equivalent to 1.645 if the probability is the area under the curve here is equivalent to 0.05. You have to look into your Z table. So we know that this one is equivalent to 1.645. This quantity here, all these things here, equivalent to 1.645. So that the probability, which is the area, the alpha area, the area under this curve representing the alpha representing the alpha is 0.05. So by some simplification, we got 6 C minus 10 here divided by 1 equals to 0.05. Then because we know that from the Z table that the Z value when the area under the curve is equivalent to 0.05 is 1.645, then we can make the conclusion that C minus 10 here is equivalent to 1.645 because the Z value that representing the area under the curve is the area under the curve of 0.05 is 1.645. So we got this quantity here. So we move 10 to the other side, so C is equivalent to 11.645. So we can conclude that the most powerful test is when the X bar, your X bar, is equals to C or greater than C, where C is 11.645. Hence, your X bar is 11. Should be the rejection region or the critical region should be 11. Should be greater or equals to 11.645. Okay, if it's the X bar here is more than 11.645 or equivalent to 11.645, then we can safely reject the null hypothesis. If it's less than this, then it falls within the acceptance region, so we cannot really reject the alternative hypothesis. So the other part is, if you want to, well, how about if you want to find the power of the test when the alternative hypothesis is mu equivalent to 15? So we need to find the type 2 error first, the probability of committing type 2 error. So the probability of committing type 2 error is equals to probability of accepting the null hypothesis when actually the alternative hypothesis is true. So in this case, we commit a false positive in here. A false negative in here because we fail to reject the null hypothesis when it's actually the alternative hypothesis is true. So because we require the acceptance region now, so we need to change the sign. So this is equals to probability of X bar less than or equals to 11.645 given the mu is 15 under the alternative hypothesis. So this can be considered as a random variable, so we can transform it into a standard into z value which is under the standard normal distributions. So 11.645 minus the mu, and then divided by the by the standard error, and then we will get this quantity here. When we will get this quantity here, so we look into the z table, and then we know that this is equivalent to a probability of 0.0004. But we don't want to know about the probability of type 2 error. What we want to know is the power of the test. So the power of the test is equals to 1 minus the probability of committing type 2 error, which is 1 minus beta. So in this case, 1 minus 0.0004. So the power of the test is 0.9996. So it has a very high power. So that's why we can consider the critical region belongs to the power at the maximum. So in this case, based on the Neyman Pearson Lemma, these critical regions preserve or fix the alpha values at 0.05 while maximizing the power of the test, or while minimizing the type 2 error rate. Okay, let's proceed to the next example. Let's say in this case we have, do you have any questions? Please respond. If you want me to go slower or you want me to go to the previous slide, just inform me if you want to copy some of the solutions there. Or you have any questions at all?
Question in class, ada soalan tak?
Any response?
Please respond.
For now, no, Doctor.
All right. Okay, so we proceed with the next example then. So in this example, we use the exponential distributions. Assume that we have a sample or a non-sample from an exponential distributions, and in this case, we have H naught with the scale parameter fixed at 2, and then under the alternative hypothesis, the scale parameter is fixed at 1. So in this case, we need to find the most powerful critical region of size alpha. All right. So how we solve this kind of equations? Again, we have to use the Neyman Pearson Lemma. So we know that the random variable x, is distributed as exponential distributions with a parameter theta, where the fx or the PDF, the probability density functions of these exponential distributions, is given by 1 over theta times exponential x minus x divided by theta, where the support is more than zeros. The support is always positive, has positive support. So based on the question here, because we fix the theta naught to certain values and the theta a to certain values, so we can consider these two alternative simple hypotheses for both the null and the alternative hypothesis. For the alternative hypothesis, the simple hypothesis, because for null we always take the form of simple hypothesis because we fix the parameter to certain values. So in this case, again, based on the Neyman Pearson Lemma, we perform the likelihood ratio test, where we look at the ratio of the likelihood of the parameter, in this case the theta, the scale parameter, theta naught, divided by the likelihood of the scale parameter theta A, and then this is given by this quantity here, fxn fx1 times fx2 times fx3 and until fxn, the joint probability distributions given the values of the theta under the null distribution, under the null hypothesis. And then this is divided by the joint distribution of x1 until xn with given the values of theta under the alternative hypothesis. In this case, under the theta equals to 1. And then theta equals to 2 for the null hypothesis. And this is equals to or less than k. Okay. So using a simple algebraic manipulation, then we will get this quantity here for the numerator. And then we got this quantity here for the denominator. And then this is less than or equals to k. Again, I put it here, I mean, as a reminder that our H0 is a theta naught equals to 2, and then our theta A under the alternative hypothesis equals to 1. Okay, so based on some simple algebraic relationships, so because this is a fixed quantity here, it's not a random variable, so we got, I mean, this one can be considered as a 1 over theta naught to the power of n, because we get the joint distribution of x1 until xn. So we multiply all this quantity until n. So for this one, it's also the same, because when we multiply these things with another quantity of this we multiply x1 here with e to the minus x1 here over theta naught with e to the power of x2 divided by theta naught until e to the power of xn divided by theta naught. So we get a summation of xi here until n and divided by theta naught. And also the same for the quantity in the denominator. And this is less than or equals to k. All right. So we plug in our theta here into our theta naught into the numerator here, into the numerator quantity here, into here, and then 1 into the denominator here. So we get these ratios. You just plug in the values. And then, so with some algebraic simplifications, and we get these quantities here. And then we bring like 2 up, then the signs change into minus. So this is the final quantities, the final quantities after the algebraic manipulation. And then with some summations in here, we will get this quantity, because xi divided by 2, summation of xi divided by 2 plus 2 summation to n xi divided by 2, we will get that positive xi divided by 2. Okay. So to solve this equation, so we take logs, natural logs on both sides. We take natural log on both sides. So this becomes a ln k, and this ln becomes a ln of this. So based on the logarithmic relationship, this will change into this one. Okay. I think this is pretty straightforward. So in this case, we can bring the quantity here from the left-hand side to the right-hand side, so it becomes positive. So you can see that now the xi, the sum of xi divided by 2 is less than or equal plus n ln 2. And then we can further simplify this. By dividing both sides of this equation of this inequality with 2. And then we will get these final quantities here. So as you can see that both n and k can be considered as constants, because these are not a random, these two are not random variables. So we can represent the right-hand side as c, as like your constant, your critical region. So the critical region for this test is given by xi divided by less than or equals to c. And then this region becomes your most powerful region of size alpha. So if you want to solve this, if you want to get what is C, then we need additional information before we can proceed further. I mean, to obtain what is C actually. All right. So I proceed to the final example, example 7. And this is just like a flavor of a composite hypothesis, in how we can solve the composite hypothesis. So we just consider that we now, in this case, we have a random sample from a normal distribution of mu, and then a variance of 36. Then we wish to test null hypothesis of mu equals to 50 against an alternative hypothesis of mu more than 59. You can take a value of 60, 61, 62, 63, or 59.1, 59.2. But it should be bigger than 59. So in this case, our task is to find the most powerful region, critical region with size of the test fixed at certain values of alpha. Okay, the type 1 error. So how we can solve this problem? So this is the solution for this problem. So because we know that the xi is normally distributed, and then it's normally distributed with a parameter of mu and then the variance of 36, and then we obtain the further information that the H0 is given by the H0 distribution is given by mu 50 with a variance of 36 for sure, and then the HA here, the value should be more than 59, and then the variance is 36. In this case, we can say that the alternative hypothesis is a composite one, because in this case the parameter is not particularly specified, because it can take any values more than 59, 59.1, 59.2, but so we don't know. So the distribution becomes a non-exact, PDF. So in this case, it can be considered as a composite alternative hypothesis. Okay, so recall that the normal distribution is given by this PDF. So if the distributions of a fixed variance at 36 is thus given by this quantity on the right hand side. We just plug in the variance into sigma squared in here, and then maybe we can plug in like 6 in here. I mean, because I just remove all the squared outside, so it becomes 6 here. But we can also put like 36 in here, but this one becomes sigma squared, and then the squared here becomes only for the numerator. So now, what is the likelihood form of this parameter? So again, using the simple likelihood theory, so it's like a joint probability distributions of xi until xn. Okay. Joint distribution of xi until xn. So we just like multiply the x1 given u is sigma squared at 36, and x2 given u and sigma squared at 36, and until xn mu and sigma squared equals to 36, and then this is given by this by these equations. So after this, then for the second step, we need to perform the likelihood ratio test based on the Neyman Pearson Lemma to find what is the critical region, the best critical region for a composite alternative hypothesis like this. So in this case, we just we try to fix the values, one single value, for example, to 60. I mean, we assume that now 60 because it's more than 59, so we assume a 60. Then we try to proceed with this method. So now we want to find the likelihood of 50, mu equals to 50 divided by mu equals to 60, less than or equals to certain constant. So we got this equation in here. We put into the numerator, and then we plug in the mu equals to 50 into the formula. Okay. And then for the denominator, we also do the same thing, where we plug in the values of HA mu equals to 60 into the quantity in here. All right. So based on because these are constant, so we just cancel out these terms. So we can use this following relationship to manipulate this side. So it should be like less than or equals to k here. I missed the k here. So it's less than or equals to k. So using the relationship in here, we can further manipulate the left hand side into this, because this quantity is the power in here minus the power in here based on these algebraic simplifications. So we got this quantity, so it's less than equals to k. So in this case, we take log on both sides and we simplify the equations. So we got these following quantities then. The k take logs on the right side, so become ln k, and then when we take log on the for this exponential term, so we'll be left with this quantity with the power of that exponential term. So now we have to we can multiply to cancel this. Then we multiply both sides with a negative 72. So it becomes a minus 72 ln k, and then this term disappear here. And because we divide both sides with a negative, so the sign change becomes this. And again, we expand the brackets in here. We expand the brackets in here, the quadratic expression in here. So we will get these quantities for the first bits, and these quantities until here, from here until here for the second bits. All right, because it's summations, so it becomes a sum of this. Okay, a simple summation relationship. So because these quantities are similar, so these terms cancel out. This term cancel out. So we are now left with this quantity only. But remember, from your mean formula, from your simple mean formula, remember that the sum of I from I to n for random variables of xi is equivalent to n, your sample size, times by your x bar, by your sample mean. And because of this, we can plug in this nx here, the nx bar here, into all these quantities here. So this inequalities becomes this, where we substitute xi here with this quantity. So it becomes like this. So after some algebraic, some simple algebraic manipulations, so we bring all the quantities to the right side. So we are now left x bar equals to 60 minus 50. Where on the right side, all this quantity here in the numerator divided by 2n. Because 60 minus 50 is a positive, so 60 minus 50 becomes 10. So we can divide both sides with 10. So this will be the final forms of these inequalities. 2n for the denominator becomes 2n times 10. Since n, again, since the quantity here k and k and here and n here and n here, they are constant. They are not random variables. So we can represent the right side as a constant c. So there's no problem to do that. So x bar is big. So your critical region is x bar equals to or more than c. So if you conduct a hypothesis test and based on your x bar, if the x bar is more than or equals to c, then we can safely reject the null hypothesis. But if it's less than or equals to c, then we cannot reject the null hypothesis because it falls within the acceptance region. So we need to accept the null hypothesis or fails to reject the null hypothesis. So in this case, we can say that the most powerful test of H naught mu equals to 50 versus HA mu more than 59 has the rejection critical region given by this quantity here. This is set theory. It's based on set notations, where the X is any elements where it's bigger than C. When the elements falls within is bigger than C, falls within the rejection region. So if it falls within this rejection region, then all the elements there can be then the quantity that you obtain there can be the basis for you to reject the null hypothesis. Where C is selected, that probability of X more than C when mu equals to 50 is fixed at a certain level, at the alpha level, which means that we preserve the type 1 error while maximizing the power of the test. So because of that, because X should be more than 60, should be 59. So if you substitute the X the mu here to 61, 62 or 63, so it all will fall within the rejection region. Okay, because this one is positive. So if you put we put 61, still will be positive. Now you put 62, it still will be positive. So it all will fall within within the rejection region. So when it falls within the rejection region, so we can say that the test for any values, any hypothetical values for HA, this test will be the most powerful test. We are at a fixed alpha level. All right. Okay, so since we have reached 11:35 here, and then we still have like another example, like example 8, 9, and 10. So if we want to carry on with all these examples, it will take lots of times, and then we may exceed 12 noon. I mean, pass your lecture time today. So I think I better stop there, and then the example 8, example 9, and example 10 can be used as practice questions. But at the same time, I will post the solution for example 8, 9, and 10 in my updated slides. After this, I will give to Dr. Muhammad Nasir later that he will distribute to all of you later on for you to check your answers, whether the answers are correct, are compatible to the model answers given in this slide. Okay. So you can do the example 8, example 9, and example 10. Okay, I will share with Dr. Nasir the slides first, but the updated slides containing the solution for these examples will be shared with you later. All right. So final words, I would acknowledge that all this. I would like to acknowledge and thank Dr. Muhammad Nasir Abdullah for providing me the original slides, which I have slightly modified and worded to increase, the clarity of the presentations. And that's all for today. Any questions from the students? Please respond.
Doctor, I have a question.
Yes.
All right. Before us, I am Nur Ala Sabrina, and I'm from group class B.
All right.
And the question sounds like this: why is the critical region always to the right side in the use of the F test? That's my question.
To the right side.
Yes.
All right. For example, for ANOVA, right, for the F test, right? Isn't it?
Yes.
Okay. Because for the F test, you have like certain quantities, like when you conduct the like, for example, ANOVA. I mean, based on the F test, you have like for the numerator is like your difference between the groups, and then divided by within the groups. So you will get your F test quantities there. So you will that's why the what I call that the F distributions is not symmetrical. Like it has like some tails on the right side, but it doesn't have the tails on the left side because it's always positive there. So so in this case, you try to fix certain critical certain critical values where you will reject the. Let me show you the, we call that the. It's better for me to show you the, we call that the F test itself. No, the F distribution itself. Wait. Okay, let me share you the screen now. Okay, wait. Where is it? Okay, type Windows. Share. Can you see this Windows here? Right? Can you see this picture?
Can.
Okay, the F distribution. Okay, as I say, it's not symmetrical. It's always positive because it has a positive support, and these are F distributions. And then that's why you fix certain alpha, I mean, you fix a certain values in here, and this will be your F values will be the critical ratios, will be the critical ratios we call that, and then because when because of the quantity that you compute for the F statistic itself, it's like I mean the between effect treatment, for example in ANOVA, between effect treatment divided by the random random variation within the groups for each group. So if you can maximize the numerator and while minimizing the random variation in the denominator, so you can maximize the F values, right? So when you maximize the F values, so the F values will always, if the treatment is always working, I mean, it has a significant difference between the group, for example. So the numerator will always be bigger than the, than the random variations given by the denominator. In this case, we maximize the F, the F quantities, and because of this, it falls. It always, if the significant difference, it will always fall within the right side of your critical ratio in here. So that's why on the right side here, and that's why the rejection region is always given by your right side for the F distributions. To illustrate it further, let me show you the F ratios. The formula for this one. For example, for analysis of ANOVA here. So for your F ratios in here, it's always it's a ratio between the group variability and then within the group variability. For example, you have like three groups, so we want to know the group variability between group 1 and group 2, group 3, group 1 and group 2, group 3, and group 1 and group 3 and group 2 and group 3, for example. And then the sum of this will be divided within each group punya variability. All right, so this is given by here. Okay. So for example, you want to fix, you for sure you have your own degree of freedom for the numerator and denominator. You have a degree of freedom there, and then you want to fix the based on the F distributions table. F distribution table. Sorry, I don't have the resource here, so that's why I have to show one by one. Yes, for the 5 percentile distribution in here, for example, based on the DF or degree of freedom for the numerator and denominator, we got certain values for the alpha. For example, if the degrees of freedom is 6 for the row, for the denominator is 6, and then for the 4 for the numerator as 4, so we can say that the critical value is 6.63. So in this case, we fix the critical value, your critical value to 6.6 something that I showed you. If the numerator degree of freedom is 4, and then the denominator degree of freedom is the numerator degree of freedom is 4, yes, and then the numerator degree of freedom is 6. So based on the F table, then we know that it's 6.6 something there. So it's here. Just imagine that the between group variability, as I said before, is bigger than the within group variability. And because of this, then this F becomes maximized. We call that becomes large because this quantity is always bigger than the within group variability. When it comes to this, when the F values becomes large, then based on the F distribution table here, so there's a higher chance for the values for the F statistics that you compute will fall in this region, right? Rather than to the region here. Because the numerator is it's always bigger than the denominator. The denominator, for example, in this scenario. So because of when it falls to this side, so it will be rejected because it exceeds the critical ratio of 6.6 something just now, 6.6 something just now. So that's why all the values where if there's a treatment difference between group difference is bigger than the within the group difference. If we get these kind of things, then the F values become maximized, and that's the reason why it falls always onto the right side, because it becomes more positive, and then it always exceeds the critical ratio, and that's why the rejection region always fall on the right side. And as I said before, the F distribution is always dissymmetrical, and then the F because it's not as symmetrical as the normal or Gaussian distribution, and because of this, it always falls on the right side because we don't have any any lines to the negative side here. So it's always on the right side. For normal distribution, it's different because it's symmetrical. We can conduct like a two-tailed test. So we can have this quantity here, and then we have another quantity on the negative side. But for F distributions, because it's based on the F ratios, it's always positive. So we don't have any any lines representing the negative sides. So that's why we can say that the F values has a positive support. So because of this, that's why it always lies on the right side. Okay. So I hope that answers your question.
Yes, I got it. Thank you.
You got it right? Okay, thank you. Any further question?
Ada soalan lain?
I'm sorry about that because I don't have the resources, so that's why I have to Google some
Okey doktor,
some
ada
images.
soalan daripada Wan Shazmin. To know the K value in Neyman Pearson Lemma, do we need to know the alternative hypothesis? To what?
Sorry?
Ada dekat message ni ada tulis.
Message. Oh yes.
To what I understood, we
Okay.
could get the K using null hypothesis and require significant level alpha.
Yes. In this case, I mean, for sure that because based on the Neyman Pearson Lemma itself, I mean, based on the example that I showed, I mean, the Neyman Pearson Lemma always say that the likelihood ratio test is the most uniformly powerful test, and then this likelihood ratio test is always based on the on the ratios of the null hypothesis against the alternative hypothesis. So so if we don't specify the alternative hypothesis to a certain value, then it becomes a composite hypothesis. So when it becomes a composite hypothesis, so so we need to, even though we don't specify the alternative hypothesis, we have to show that in this case, at least for a certain value of alternative hypothesis based on the last example I showed just now, that this is the most uniformly powerful test. And then based on this, then we can get the K values, the constants. We call it the constants. See the constants. So in this case, the alternative hypothesis, even though we don't really have a value for this one, we need to specify certain values just to prove it, that the values of the constant that will represent the critical represent the critical ratio or the critical value for demarcating or for setting the boundaries for the critical region can be obtained. So in this case, even though you don't know the actual values of the alternative hypothesis, but you can hypothesize the alternative hypothesis based on certain assumption. For example, like based on the example I just showed you now, because I said that the mu is more than 59, so you can show that the mu under the alternative hypothesis equals to 60, or you can use different values like 70 or 59.1. That's fine as well, because once you show it once, based on the mathematical proof by using mathematical proof. In this kind of proof, we can show that the critical region lies between certain limits, lies between certain inequalities, and because of this, we need to, if we don't have the value for the alternative hypothesis, we need to at least assume the alternative hypothesis to obtain your constant. Yes, I think that's my take on this. And then if it's Dr. Nasir has different views on this, I mean, he more than happy if he can share the answer as well.
I think Dr. Irfan explained well.
At least you have to assume. You have to assume it, because I mean, if you don't assume the alternative hypothesis, I mean, based on certain restriction for some mu more than 59, if you don't assume it, I mean, we cannot like really prove and then obtain the K, or the constant. You cannot set the boundaries for the for the rejection region. All right. All right. There's another questions. Oh, all right.
Maybe this one is
To ask
last question, Dr.
Okay, so I want to ask how to get the value for V1 degree of freedom in the F distribution table, because some F distribution table doesn't have the value of T1 goes to 11. Okay, this is kalau nak cakap pasal benda ni, I mean, it's going to be a very long story, yes, actually, because based on the historical accounts, the F distribution tables, because the ANOVA, this ANOVA method has been promulgated or has been created by R.A. Fisher himself. And everybody knows R.A. Fisher, the Fisher exact test and everything. I mean, he is the one, the master of this, of this ANOVA stuff. So because of the space limitation in the books during that time, and then you have to calculate the probability, using Hens calculation at the time. Using a Hens calculation at the time, so that's why I mean the degree of freedom is restricted to certain, to certain values for the numerator and denominator, because of space limitation. At the same time, the task was pretty arduous because you have to do it manually. So nowadays, I mean, to obtain the degree of freedom of more than certain values, there are two ways you can do that. I mean, for sure, you can buy a better books that contains a better table that contains a degree of freedom more than 11, for example. Or again, because you are a statistics student, for sure you are, you are exposed to certain programming language like R, all those things. You can always, get this information from the program itself, So you can get the V1 degree of freedom in the application because some doesn't have the value for V1. Is it the values for the, is it the F values, right? If I'm not mistaken here, I got the question wrong. Get the value for V1, yes, the F values, right? Okay. So in this case, you have to resort to certain free software, like free programming language like R, and then using the function in R, you can plug in the alpha level that you want to fix, like 0.05, and then at the same time you fix, you can say that okay, the degree of freedom for your numerator is this much, for example like 11, and then the degree of freedom for the denominator is this much, and then from this one, using the software, when you click, then it will give you the values of the F ratios based on the degree of freedom that are not contained, that are not given in the table. And that's the quick and dirty way, I say, the quick and dirty way to obtain it. But why the reason why it's limited to, for example, like 10 degree of freedom 10 in your current table is because of the space limitation, historically because of the space limitations, and at the same time because of everything need to be calculated manually. Because there are all these previous statisticians, the old timers, I consider them as old timers, they calculated everything manually. So they cannot like calculate it for for degree of freedom 11, 12, 15, and so on and so forth. They will not stop. So that's why they have to restrict to certain values for degree of freedoms, and that's why they also like restrict to the certain values of alpha, like alpha at 5 percentile point, and then alpha at the 1 percentile point, rather than showing the alpha at the 7 percentile point, 8 percentile point, 10 percentile point, 12 percentile point, or 0.0001 percentile point, because of space limitations. But because now we are in modern days, and thanks to the development of R and other and other softwares, I think you will be learning this soon. Or you might be learning now, then you can plug in the, use the function in R to obtain the F values based on the degree of freedom that you want to specify, 11, 12, or 13. I think that's the pretty quick and dirty way to obtain the F values, from my opinion. But Dr. Nasir found another table. Maybe Dr. Nasir can share with all you with a standard F distribution table, which is better, I think.
Alright, thank you Dr. Muhammad Irfan. I think untuk soalan tadi tu mungkin kalau dalam final exam kita tak tanyalah soalan yang keluar daripada boundary statistical table kita lah. So kalau tanya juga tu mungkin you extra hard question lah saja nak bagi you susah sikit kan. Tapi always you can integrate the distribution to dapatkan the value kan. Okay, I think this very impressive lecture from Dr. Muhammad Irfan, and then I as lecturer in STA 256 mewakili juga dengan Puan Nur Faizah Jamal as a lecturer in charge STA 256 in UiTM Tapa. Mewakili juga dengan Puan Nur Aisyah di Negeri Sembilan, UiTM Negeri Sembilan, mewakili resource person. Right, we would like to express our biggest thank you for Dr. Muhammad Irfan for his effort and very informative lecture on Neyman Pearson Lemma. And I hope students can understand the topic very well, since this topic will be on your next assessment next week, right? So if you have further question, right, you can always ask in a WhatsApp group, right? So I think that's all. Thank you very much. And before we end our session, can we just take a very quick picture untuk gambar sama selfie? Boleh tak Dr. Irfan unshare dulu?
Okay, alright.
Unshare,
Sorry
and
about that.
student,
Okay.
please make sure you switch on your webcam. Kita tunggu sikit lagi, ada yang belum lagi. Fatin Alia, Arina, Izati, Nur Akila, Nur Kamilia, Aisyah Safia, semua tolong switch on your webcam. Okay. Kita selfie Kejap Alright. 1, 2, 3. Okay, another one. Kejap. Right. 1, 2, 3. Okay. So on that note, thank you very much, Dr. Irfan, and students.
Thank you for inviting me, Dr. Nasir. Thank you very much.
Okay, Assalamualaikum.
Assalamualaikum warahmatullahi wabarakatuh.